Today we're seeking a maximum value for what turns out to be fourth degree polynomial. Now the nice thing about the approach I'm showing you today, this is fourth degree polynomial, DEG we'll call it. And of course it's fourth degree because you're composing a second degree or a quadratic expression with itself. So P of x will definitely have x to the fourth as its leading term. It'd be x to the fourth and then plus a lot of other terms, okay, which turn out not to be important. And so we want to look for a maximum, a local, some people call it relative maximum value. Now, what we're going to utilize here is something called end behavior. You guys know that a fourth degree polynomial might look something like this. You know, it's going to have 1, 2, 3 turning points. So we're anticipating something like this if you want to trust the instructions. Notice you have 1, 2, 3 turning points, which is a property of polynomials. It's fourth degree, but you have 1, 2, 3 what is referred to as turning points, and those are actually where you can have local mins and local maxes. So we're looking for this point here. There may be other behaviors here, but this is kind of a typical behavior of a fourth degree polynomial. It's called end behavior. Now towards that, the part that I like about this problem is you never really have to expand it out. You just physically substitute P of x back into the original polynomial. All right, and I wrote this in just for clarity. P of x means P of x quantity squared minus 9P of x plus 17. This is a good way to teach people who are just learning it. And then you do your substitutions. Now it's tempting here to actually expand this out and work with a fourth degree polynomial, maybe take derivatives, look for critical points, all that kind of stuff. But it's actually easier, in my opinion, to do something called completing the square. You'll notice here that 9/2 quantity squared is 81 over 4. And after you complete the arithmetic, you end up with this expression right here. You guys can check the arithmetic right here. This would be 68 over 4 minus 81 over 4, which is minus 13 over 4. All right, now notice at this point, you can't really figure out what the max is unless you factor. So if you'll notice, this is actually, I'll put 1 there. So you have this factor, this entire object here is common to both terms, and so you can actually factor it out right here. And you see how we're actually getting a product here. It's kind of an unusual looking greatest common factor, but it's a greatest common factor nonetheless. So you see now that we have a product here, we can easily identify x equals 9/2 is the point where you're going to have this local maximum value. So for x equals to 9/2, okay, and that would be the x coordinate of where this max is going to occur. Now this is a little strange because if you put 9/2 in here, you get minus 13/4, which is a min, right? Just if you consider this term alone, but you're doing it to 2 of them. Okay, you're doing that to two of them. And so when you actually multiply 13 over 4 times 49 over 4, you get, I believe, 637 over 16. So you would end up with 637 over 16. Again, you're taking the product of 2 negative numbers. That's what makes this a little counterintuitive. So the product of 2 negative numbers is positive. That product is this, and then you still have the plus 17 hanging around here. Okay, now let's see here. This is equal to 17 times 16 is 272. So you end up with 909 over 16. Okay, and there's no doubt that this would be a local maximum value because if you substitute any other numbers in other than 9/2, you're going to be adding the same positive number to the negative number. And you see, even though it's getting to be a larger negative number, the product is still positive, right? So it's definitely the case that the local max would happen at the coordinates 9/2, and then the maximum value would be 909. Now I'm not giving, this isn't really what I would call a super rigorous proof because I'm not telling you the neighborhood, but I don't really have to because, you know, we know that we know that the behavior of a quartic, in the end, it just looks like any other squared monomial, right? But in between, you're going to have the wiggling around because of the zeros and also the turning points, all right? And so we've located this point right here. In other words, this would be the point that we just found, 9/2 and 909/16. So that is a local max, meaning it's only as big as it can be in a neighborhood. Obviously, it goes to infinity in both directions. But in this neighborhood here, and you could actually take the time to find these points if you wanted to determine these are the mins. You know, you might, I'm not sure, you might have to use calculus for that, and maybe there's other ways, Cauchy-Schwarz or something. But anyway, we have met the requirements of the problem right here. So this is the answer. And again, completing the square in fairly rudimentary algebra got us there without having to appeal to calculus or anything too sophisticated. Thank you for viewing.